There is a reception up on level 2. Yes, level 2. Thank you very much.
Reception. We were kind of told there was something upstairs. So we go.
I would say nobody can give you a definite answer right now. Some people think that there is a real boundary. One of the things as an experimentalist, I like one of these ideas is that there's some physical process that we haven't clearly identified yet that for certain size systems will give rise to this boundary between the quantum world where we have superpositions and the classical world where we don't. But that's, I think that's clearly just speculation. So I personally think this is one of the big mysteries in science, is we don't have a way to resolve this problem. That is why, we aren't in superpositions ourselves, and of course, extreme solution to that is, well, we are in superpositions, as I do many universes, many worlds. So I think one of the very interesting questions for the future is to resolve just this problem, the fact that we don't really have a way to define this boundary, and maybe there isn't one. Actually, one of the things that's always kind of disappointing to me is that after all my well, money always helps. It's required to fund the research we do, but I think it'll be maybe a combination of that, being able to do more sophisticated experiments, but it'll almost undoubtedly involve some clever thinking about how to view this problem. But as I say, I think this one of the things that make this really interesting, and this problem, to my mind and to many people's mind, is unsolved right now. So the Earth, for example, in Boulder, partly because of the mountains, the uncertainty in the height is, in terms of its gravitational potential. A good example is the laser. When the first lasers were made, nobody realized all the things that would be used for, and I think very likely we're in the same situation with these ideas of quantum information or quantum computing, is that, we have this one killer application, this factoring machine, but very likely the real applications are ones we haven't thought of. But having said that, I think on the shorter term, I think what most physicists think about is this idea that it comes from Richard Feynman, one of the early people to think about quantum computers, is that maybe we can get one quantum system to mimic or simulate, we say, another quantum system of interest. And I think most of us are at least optimistic that we will find a quantum simulator that not only we have small ones now, but they're small enough now that we can simulate what goes on with a classical computer. And I think the exciting thing is that I think most of us are optimistic that, at least maybe not in the too far future, that we would get a simulator, a quantum simulator, that will tell us something interesting that we didn't know before. And that will come, I think, at least from our understanding now, that will come way before a useful quantum computer is made. Over the years, we certainly relied on very large numbers of good students of the fundamental particles, the gluons and quarks that make the elementary particles, and then those particles that combine together to, these systems can't be simulated efficiency because of this problem of exponential scaling. So that's one area where people are thinking about. Another example might be, in this a little hard to see maybe now how this works, but for example, as people make drugs, which are big molecules, maybe a potential use of a quantum computer might be able to simulate their behavior without having to make them, to be able to predict their properties. But so it's those kind of things which are, still yet to be realized, but I think are are potentially real possibilities that might, might really be a useful application of quantum computers.
A very fancy deal on this one. This is a once-in-a-lifetime thing for certainly most physicists. And
There's various proposals, theories put forward that, for example, maybe the fundamental constants which describe the strength of the various fundamental forces in nature, possibly they might be changing in time. And, so far there's no overwhelming reason that should be the case, but with these very accurate clocks, we can actually test these ideas at ever-increasing levels of precision. And if we found that to be the case, that would be a very fundamental discovery and would change how people formulate the theories that concern the basic forces in nature. On a much more practical scale, certainly clocks throughout history, for many, many centuries, their main function has been for navigation. And we kind of take for granted these days the ability to navigate sort of on the meter level of precision with GPS, and that's one example where atomic clocks have been important because they're they're on board the satellites that are used in GPS. So you could argue, well, if we can navigate to a meter, that's pretty good, but an example where even more precise navigation would be used. One popular example is that more precise navigation could be used to measure displacements of position on the Earth, on the millimeter level of precision, and that potentially is very important, for example, as a predictor of earthquakes. The fact that the Earth will stretch or contract in locations depending on before an earthquake happens. And so that would be one application that people look forward as we get better and better in terms of the clocks and their navigation abilities.
it's almost surreal experience for us to receive the award from that.
No, as far as we know, no. So it's a matter, there's some, when we compare clocks, there's certain fundamental noise processes that we say that require us to compare the clock rate, the tick rates of different clocks. We need to compare them for longer units of time to get high precision. But other than that, we say we're kind of averaging over the noise and there's some fundamental sources of this noise. But other than that, having to maybe average or compare the clock, the rates of two clocks over longer and longer times, we can always reach, in principle, arbitrary precision. So as far as we know, no, the answer is there shouldn't be any limit to how precisely we can make time or do these comparisons.
Not surprisingly, it's a very important event for, Swedish society and official now.
I probably do take a very practical on the view on that. It's a way to order events in some logical way, and I think anybody's notion of time is probably as good as any physicist's notion of time. It's just a way to order events in a logical way, and I think that's the way most of us feel, and most of us physicists. It has that same application for us too.
Meeting on the same weekend, anyway, thanks everybody for coming.